Okay. It's a sad occasion today to be speaking about Jerzy Lewandowski. I met Jurek first as a brilliant postdoc, but then very quickly he sort of grew in stature to become an inspiring colleague for me for many, many years. And then also during this period, he became a dear friend both to me and my family. So I'd like to sort of cover very briefly all these aspects of Jurek. So my 30 plus year collaboration with Jurek really began when he joined my Syracuse group as a postdoc on a Fulbright fellowship. And we published our first paper in 1993. And we had just begun to work on a joint review article with Maciek, which was commissioned by the British Institute of Physics at the time of Jurek's untimely death. So it has been a long collaboration spanning many topics. And when I heard the news from Ella about Jurek's passing, I was in a total shock. My mind is still flooded by innumerable memories. In the limited time I have, I thought that the best way to express my emotions is to recall what David Hilbert said at the untimely loss of a junior colleague and dear friend, Herman Minkowski. That way, I will be able to be succinct because Hilbert's thoughts really capture my sentiments very well. So here is what Hilbert Space said on the untimely passing of Minkowski, and it really completely mirrors how I feel. He said, "Our science, which we loved, had brought us together. It appeared as a flowering garden. In that garden, there were well-worn paths where one might look around at leisure and enjoy oneself without effort, especially at the side of a congenial companion. We also liked to seek out hidden trails and discovered many unexpected view, which was pleasing to our eyes. And when one pointed it out to the other and we admired it together, our joy was complete." These words really capture the hard work that Jurek and I did over the more than 3 decades when we actually discussed many, many things together and found unexpected vistas in the process. So let me give you a few examples of these hidden trails that we had the good fortune to discover together. The first comes from general relativity as a theory of connections. And this part really lies at the heart or foundations of loop quantum gravity. So this began with the notion, with the idea that general relativity can be really regarded as a theory of connections, as I just said. And Chris Isham and I had realized that, in fact, an appropriate space of connections is not going to be the smooth connections, but we should really emphasize the holonomies that are defined by the smooth connections. These holonomies are functions of connections, and therefore they form a certain abelian star algebra, abelian ring of functions, if you like, and that can actually be realized as a space of all continuous functions on some space, which is called the Gelfand spectrum of the holonomy algebra. Now, for the longest time, there was a belief that there would not exist any diffeomorphism invariant measure on the space of all connections. But then with this realization that what we should be focusing on is really the Gelfand spectrum of the holonomy algebra and not smooth connections, the problem changed completely. And although there was this deep skepticism among many mathematicians that a measure could exist, Jurek and I found this invariant measure, and that was our good fortune to discover a completely unknown vista. Next, because the space of generalized connection A is a Gelfand spectrum of the holonomy algebra defined by smooth connections, it has a lot of properties, and thanks to Jurek's great mathematical insights, we discovered that one could do differential geometry on this space of algebras, on this the Gelfand spectrum on this space of generalized connection. And for example, discuss forms on it, not only measures, but forms on it, vector fields on it, even a Laplacian type operator on it. And that really made available a whole new bunch of techniques that have been exploited very successfully in loop quantum gravity. And these techniques then led to what I called here the quantum Riemannian geometry that constitutes the foundations of loop quantum gravity. In particular, Jurek and I found independently the area and the volume operators. And in fact, I was just around that time, there was a volume being contemplated to honor Andrei Trautmann. And so Jurek and I actually held on to this paper for a year or two so that this actually appeared in a volume honoring Andrei, because I very much wanted something which was important, which was something that was nice in this article. And so these papers really constitute a basis of a lot of things that have happened in loop quantum gravity. Second thing was really, although our main idea came from gravity, because in fact, we are looking at gravity as a theory of connections, we could apply these ideas also to just gauge theories. And then there was a joyous connection, joyous collaboration, a joyous alliance, which was very tightly woven, that formed at Penn State, and it's called ALMMT. It was me, Jurek, Lewandowski, Marolf, Morau, and Tiemann. And here you see a picture of all of us in the alphabetical order in which ALMMT appears in a conference. And there we found the mathematical foundations of how to do quantization of diffeomorphism invariant theories of connections with local degrees of freedom. Topological field theories of this kind were known, but we were looking for local degrees of freedom. And then, as I said, although our main motivation came from gravity, we could apply it to gauge theories by themselves. So we found, for example, a closed formula for Wilson loops for SUN quantum Yang-Mills theory in 2 dimensions, which was a new result at the time. And also, we found what is known as a coherent state transform. So let me just step back and say what this is. In ordinary quantum mechanics, we got Schrodinger representation, but long time ago, Bargmann found that in place of looking at states as being functions on the configuration space, you can also look at them as functions on the phase space, but then we have to look at them as holomorphic functions. Bargmann, of course, just considered finite dimensional spaces and vector spaces as phase spaces, and that is a Bargmann representation. Then Brian Hall, a mathematician, generalized them and did the Bargmann representation, if you like, on compact Lie groups. So it's still a manifold, but it's finite dimensional. And what ALMT did was really to generalize it to the space of connections. So it's really to generalize it to the infinite dimensional spaces of connections. Third collaboration, which also led to new vistas for us with Jurek, was dealt with quantum cosmology, namely, first, the mathematical foundations of loop quantum cosmology. Ideas of loop quantum cosmology had been sort of spelled out a little bit, the very first ideas, but as is often the case, the first ideas are rough and they don't completely, there are some flaws, they are not free of defects. And in fact, there was a workshop in the Schrodinger Institute in Vienna where Martin Boyewald gave a talk, and then there were a lot of reservations expressed by people like Bill Unruh and so on. So already at that workshop itself, we got together and we started discussing very intensely how to overcome the objections that were raised. And we realized that what was needed was not to use the Schrodinger type quantum mechanics that was being used for loop quantum cosmology, because it's a system with finite number of degrees of freedom. And that quantization was what was used in the Wheeler-DeWitt theory. But really, we need a new kind of quantum mechanics. And this new kind of quantum mechanics had already been discussed by Buchholz and Fredenhagen. We didn't know about it, but we separately discovered it and then applied it to loop quantum cosmology. And this is the mathematical foundation on which loop quantum cosmology still rests. A second application, which came many years later, but still more than 15 years ago or so, and that was a joint work with Wojciech. And that was really about doing quantum field theory on quantum cosmological spacetimes. So the mathematical foundations of loop quantum cosmology led to a whole bunch of developments in which we realized how to discuss the geometry in the very early universe near the Big Bang using quantum geometry rather than just the classical Riemannian geometry of Einstein's. And so what we now need to do is to really develop quantum fields, quantum cosmological perturbations, for example, which will be propagating not on a smooth metric manifold, but rather on this quantum geometry, where we got probability amplitude that the metric is this, that, or the other. And this work was also sort of, to me, very, very illuminating. It opened completely new vistas. Again, going back to Hilbert and Minkowski, this was a panorama that opened up that Jurek and I looked at it and showed it to each other, and we admired it together. And finally, there were several topics in classical general relativity. I have just selected two. The first had to do with horizons, particularly the geometry of generic non-expanding horizons and the first law of quasi-local horizon mechanics. And this was a joint work with Chris Beetle. And I selected this topic because the geometry of non-expanding horizons, that paper, I'm using it even currently in my work that I've been doing right now. It has had a long life, and to me, it is full of ideas, and many, many of these ideas came directly from Jurek. So I'm so grateful to him. I kept telling him that repeatedly through emails. And finally, the emergence of the Bondi-Mesner-Sachs group, which is ascribed from the non-expanding horizon structures. And this was much more recent work. It also uses this work that I referred to about the geometry of generic non-expanding horizons. And this work also, these two papers are separated again by 15 years or so, actually 20 years or so. So with this, I conclude my scientific discussion. And now let me just mention that scientific discussion about projects that Jurek and I had done together by reminiscences of the beautiful things that we found together. But Jurek also made other pioneering contributions with members of his group, and these were to the problem of black hole entropy, to spin forms, the near horizon geometries, asymptotically de Sitter spacetimes, and algebraically spatial solutions. And these are very valuable contributions, and they were recognized by a number of international honors. In particular, Jurek's stature in the field led to his being invited to be the chair of the local organizing committee for the GR20 and Amaldi 10 meeting, which was held in Warsaw. So Jurek was absolutely the central figure for these international conferences to be brought to Warsaw. Jurek won the senior Forschungs Prize of the Alexander von Humboldt Foundation. It's a very prestigious research prize. And he was elected as a fellow to the International Society on General Relativity and Gravitation. And he has held visiting professorships at Beijing, at the FAU in Germany, and at PSU in the United States. That is a Penn State at the United States. Jurek really cared deeply for his students and postdocs and younger colleagues. And he was always discussing passionately science with them wherever he went. It could be in mountain hikes, it could be on a beach, it could be on sea slopes. So here is a mountain hike in China on the left picture. The middle picture is Jurek in the United States beaches, and the right picture is Jurek on the ski slopes of Tux in Austria. And again, I mean, this is something that epitomizes Jurek's passion for science, and that is best described. I return now to what Hilbert Spade said about Minkowski, because it really captures Jurek's spirit very, very well. Hilbert said, science was at all times interesting to him, and in no part fatigued him, whether on an excursion or on or during the summer holidays, in an art gallery, or in a railway carriage, or on the sidewalks of a big city. And we see the examples of the same thing, whether on a mountain excursion or on a beach or on the ski slopes. Jurek was always discussing science passionately with his junior colleagues. And then I come to the last part, that is, Jurek became a dear friend to me and my family. So through our close interactions, Jurek transitioned from a brilliant postdoc to an inspiring colleague in the 90s, and very soon thereafter, he became a close family friend. To me, Jurek was like a younger brother. To her son Neil, he was always Uncle Jurek. The delightful wooden St. Nicholas that Jurek brought to us from Poland. It's a very beautiful handmade little sculpture, and that graces our fireplace mantle during every Christmas since then, even now. And Jurek also gave a husky puppy to our son, who was then 4 years old, and Neil immediately nicknamed it Jingles, and often slept with Jingles, very often slept with Jingles all night. And this husky puppy up here, which is Jingles, still with us 22 years later. So let me conclude. I miss you dearly, Jurek. I carry vividly memories of the times we spent together. They were always intense, sometimes fighting, especially when it came to administrative matters and science. We did not always agree, but we didn't hesitate to express our disagreements to each other, because I think honesty was very important in our relationship. And above all, I miss the joy that we shared while admiring the new vistas that emerged from our calculations on blackboards. I also carry fond memories of the time I spent with you in the company of Ella and Pavel. I remember many restaurants. Pavel at the time was in a vegetarian mood. And so we went to new Indian restaurants that he found several times. And Ella and Pavel have been in my thoughts constantly. Thank you.